In this video, we're going to talk about two very special types of sequences, bounded sequences and monotone sequences. And you will see that these definitions are going to look very familiar to things that we have seen before. So let's get started. If you remember, before we defined what a bounded above set was, we said that set X was bounded above if there exists some real number B, such that for every X in X, X is less than or equal to B. So now we want to do an analogous definition for sequences. So we're going to say that the sequence an is bounded above if there exists a real number b such that for all n in the naturals, an is less than or equal to b. So what we're saying is that all the elements of the sequence are less than or equal to b versus all the elements of the set in the definition for set. And here, here I have a sequence, and you can see that, for example, here we have an upper bound b, but we could find any number bigger than b would also be an upper bound. And I want to leave for you as an exercise to write a definition of a sequence is bounded below. Very similar to what we did for sets. Okay, and now a bounded sequence. So we said that a sequence is bounded if it's both bounded above and below. So that means that I can find two real numbers, a and b, such that all the terms of my sequence are between a and b. As you can see here in this picture, I have a at the bottom, this yellow line, b is this blue line, and all the terms are trapped in between. And some of the elements are allowed to be equal to a or b, because if you see, our inequality says less than or equal to. Great. An equivalent definition of bounded sequence is that we say that a sequence is bounded if there exists a positive number m such that the absolute value of an is less than or equal to m for all n's. So we can create a band that traps all the terms, and I will leave for you as an exercise to convince yourself that these two definitions are equivalent. So you have to show that the first definition implies the second, and then the second implies the first. One of the two directions is very, very easy, and the other one requires a little bit more thinking, but it's not that difficult. Okay, now let's take a look at examples. Every time that we learn a new definition, it is always a good idea to see examples and non-examples. So, for example, the sequence given by 1 over n is bounded. It's bounded above, right, by 1, bounded below by 0. And the sequence given by minus 1 to the n is also bounded. It's bounded above by 1 and bounded below by negative 1. And then things are not bounded. Like if you look at the sequence like n squared, like it keeps going up and up and up and up and up. And it's impossible to find a real number that is larger than all the natural numbers after squaring them, right? And, well, we also have this one, like negative 1 to the n times n. So what it'll do is go up like positive, negative, positive, negative, positive, negative. Then you will get something that goes like up, but also something that goes like down. So it is impossible to bound it. It's impossible to trap it into two like lines. It will always escape. So these are two non-examples, things that are not bounded. So keep them in mind because in the future they're going to be quite helpful. Now we're going to take a look at some definitions that would lead us to define what is a monotone sequence. So we say that a sequence is increasing if for any natural number n, an plus 1 is greater than or equal to an. What this is saying is that every term is greater than or equal to the previous term, which agrees with our intuition of things going up. And an equivalent definition is that, well, if we know that m is less than n, then am is less than or equal to an. This is just like the definition we wrote for increasing function. If you don't believe me, just try to convince yourself. And then a decreasing sequence is, well, one that every term is smaller than or equal to the previous one. So that means that an plus 1 is less than or equal to an. Or equivalently, if I know that m is less than n, then am is greater than or equal to an. And here I have an exercise for you. I have 4 sequences, and I want you to determine whether the sequence is increasing, decreasing, both, or neither. So I invite you to pause the video, think about them, and then when you come back, you will be able to check your answers. But please, please, please try it before you continue watching the video. Welcome back. Did you get them all? Okay, let's take a look at the first one. The first one we have 1, 4, 9, 16, 25. It seems that this is actually tells us that the general term looks like n squared. And we know that one, well, the values we can see they keep going up. So this one is increasing. What about the ones that constant sequence 2, 2, 2, 2, 2, 2, 2? Well, if you say neither, you are not alone, but you are not correct. If you look carefully at the definition, the inequalities are not strict. It says less than or equal to, greater than or equal to. So 2 is less than or equal to 2, and 2 is greater than or equal to 2 because they're equal. So in this case, the constant sequence is both increasing and decreasing at the same time. I know it feels like mind-blowing, but that's what the definition is telling me. Okay, and let's take a look at the next one. We have 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. So it looks like the general terms like 1 over n. We can see that the values are getting smaller and smaller every time. So this is a decreasing sequence. I'm sure you got that one right. And what about this one? 1, 0, 1, 0, 1, 0. You could say, well, it goes up and down, up and down, up and down, up and down. So you might be tempted to say that it's both increasing and decreasing, but that would be wrong. Because if you look at the definition, it says that for any natural number, an plus 1 has to be greater than or equal to an for it to be increasing. But you see, if you pick the first term, 1, it is not bigger than the next term because it's 0. So it cannot be increasing. And now if you look at the second term, the second term here is 0, right? And, well, it is smaller than the next term, so it cannot be decreasing either. So this is neither. It's neither increasing nor decreasing. So whenever you have to check something, it's very important to carefully look at the definitions because sometimes our intuition could, play against us. We have an intuition of things increasing, like going up, decreasing, going down. But here, because we haven't less than or equals to or greater than or equal to, being equal also works for the definitions. Then that's why the constant function is both, constant sequence is both increasing and decreasing at the same time. Perfect. Now we're going to define what a monotone sequence is. Monotone sequence is a sequence that is increasing or decreasing. And remember, in math, or is inclusive, so that means that it's increasing, decreasing, or both. All those cases, we say that the sequence is monotone. So for us, the first 3 sequences in our exercise are monotone sequences. Now, let's take a look at another definition. It's strictly increasing and decreasing. This really will force our sequences to go up. So we say that it's strictly increasing if a term is strictly bigger than the previous one, and the same thing with strictly decreasing, that each term is strictly less than the previous one. And in this case, for example, a constant sequence wouldn't be strictly increasing or strictly decreasing because we are not allowing the possibility of it being equal. And now I want you to complete this exercise and take your time. It is very valuable to try to play around with all these definitions, and the best way to really understand them is to come up with examples yourself. So here we have combinations of like monotone bounded, monotone not bounded, not monotone and bounded, not monotone and not bounded. And I want you to, for each combination that you see in this table, so we have 8 combinations, try to come up with a sequence that satisfies all those properties. So try to come up with a sequence that is monotone, that is bounded, and that is convergent, and so on for all these combinations. And if you cannot find an example, then try to convince yourself that it is absolutely impossible to find such example. Please make sure that you complete this exercise before you continue watching the next video. Otherwise, you're going to have a big spoiler.